11.3, we are still dealing with waves, but we're going to get a little bit more specific here with sound. So how does sound travel? How are you able to hear my voice right now? So sound waves, first off, they are compression waves, or also remember, they're also known as longitudinal waves. This just means we're able to hear sound because all it's doing is it's vibrating particles. So that vibration is passing through the different particles in the medium. Speed of sound. Speed of sound, you don't technically really need to memorize this, but just to, like lightning and thunder. Lightning and thunder happen at the exact same time, but you're able to see the lightning before you hear the thunder because if you remember, the speed of light is like 3 times 10 to the 8th meters per second. It is extremely fast, so you can see the lightning before you hear the sound that it creates because light travels a lot faster than sound. Now, this is at 20 degrees Celsius in air. So speed also depends on the type of medium, meaning what is it traveling through. Remember, medium is what it's actually traveling through. Faster through solids. Why? Remember, long time ago, we talked about solid liquids and gases. Solids are more dense. Therefore, that vibration can go from one particle to another very easily because they're closer together. Now, no medium means no sound. No sound can travel. No medium, no sound, because it cannot travel through what's called a vacuum, and a vacuum means there's no medium there. Okay, all the substances have been sucked out. Space, outer space is a vacuum. There's hardly any particles from one point to another. Therefore, if we were in space, not talking with walkie-talkies or headsets or anything like that, you would not be able to hear me talking to you because there is no particles to vibrate between one source to another. Now, temperature is another one. So speed depends on what it's traveling through and the temperature of it. The faster, it moves faster through higher temperatures. Again, why? Why? What do we know about temperature? Temperature means that the particles are already moving faster. The higher the temperature, the particles are already moving at a higher rate. Therefore, the sound will be able to move quicker because of the particles moving quicker. Okay? So going back, type of medium and the temperature changes the speed of sound. No medium, no sound. Now, we need to take these words that we know about sound and how that relates to the wave itself. First one we're going to talk about is pitch. What is pitch? It's how high and low a sound is. So high, low a sound is. What is causing my voice to go high and low? What is changing from what's changing about that wave to cause that? And that is this. So look at these two. This is a low pitch, this is a high pitch. So low pitch, low, high, low, high. It's because if you look at these pictures, this one only has one long wave, this one has short bursts of waves. It depends on frequency. Depends on frequency. The lower the frequency, the lower the pitch. Low, low frequency, low pitch. High, high pitch, high frequency. Okay, now our ears only pick up a certain frequency. If it's too high, like a dog whistle kind of thing, your ears will not be able to pick it up because it doesn't fall into that range. This also changes with age. The older you get, the less you can hear. Okay. This, you have music notes, which is just showing you that exact correlation between pitch and frequency. So if you notice right here in your scale, these notes are going up. This is showing you have an increase in pitch. This increase in pitch correlates with an increase in frequency. If you were to if you were to draw out the waves themselves, you would see that the waves are getting closer and closer together. Okay? Next, we need to talk about intensity and loudness. Intensity is the volume of sound. It's measured in decibels. We're not doing any math with this here, okay? So intensity is the volume of sound. So you can hear me, blah, blah, blah. Or bah! Blah, bah! Okay? What you need to know is what's causing that. Why are you hearing a whisper versus me yelling? Okay? What's causing that? Now, this is loudness, but loudness is a perception. So something loud to me could be something different to you. Like the music that y'all play I could never play music that loud. Okay? So it all depends on how you perceive that sound wave. But both loudness and intensity depend on amplitude. Amplitude, that's going to be the key thing here. So intensity is the actual volume of sound, which can be measured. Loudness cannot be measured. It is a perception on how loud or how loud it is. Okay, both though are measured by amplitude. It depends on amplitude. So a whisper, there's hardly anything there. But if you talk really loud, you get a higher amplitude. Now, this can be visually seen. If you've ever done or seen on your radio where it does like this, it has like little things that go like this when the music's going, kind of thing, and it'll go like that. Screensavers and things like that used to have them on the computers. You might have it on a radio. It has little things that go up and down depending on how loud something is. That is visually showing you that amplitude increasing and decreasing when it gets loud and soft. Okay? So, loudness and intensity depends on amplitude. The higher the amplitude, the louder it is. All right? So, higher the amplitude, the louder it is. Okay, higher amplitude, louder. So I should be able to give you a set of waves. You tell me which one is the loudest. This is just showing you a threshold of the decibels versus the different types of sound. So a whisper is barely at 10, and then you get rock music, jet engine, threshold of pain. So most people cannot withstand over 120 decibels. Anything higher than that can burst your eardrums and all kinds of stuff. Okay, so this is just showing you that visual. The more decibels that it has, the louder it is. So whispering versus a jet engine. All right, Doppler effect, vocab word, is the change in wave frequency. So it's the change in wave frequency caused by a moving source. The most common thing here is a siren. All right, so just as I'm talking, mentally think of hearing a siren going past you as you're standing on the street. Okay, so when the siren is moving towards you, this picture is showing you, visually showing you, as it's moving towards you, you have compressions. So you have these tight, compact compressions going towards you. So you have frequency is higher. So towards you, as it's going towards you, frequency is higher. Going towards you, frequency is higher. As it moves away, as it's going away from you, you can visually see it again in this picture. Away, you have a low frequency. All right, so I would probably draw something very similar to this, like a stick person or whatever. And forward, you have tight. Afterwards, you have low frequency going on. Okay, so as it's moving toward, you have high frequency. As it goes away, you have low frequency. So it will literally sound like it's gotten a deeper pitch as it's moving away from you. So as it's coming, it'll be near, 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 and then as it leaves you, kind of thing. Okay, so next time you see a siren going past you, concentrate, think about what's happening to that sound as it's going by. All right, so towards you, high frequency, away, low frequency. Now, one last thing here, just some kind of extra information on how we use sound. So seeing with sound, how are we able to do ultrasounds and things and sonar and things like that, is because we are literally throwing these sound waves at these objects, and what's happening is we're getting this reflection back of how far those waves moved. Okay, so when you do an ultrasound, it's throwing frequencies at the stomach, at the uterus, and it's bringing this reflection back of where it hit the object, and we know how far things are away from each other and things like that.